Have you ever stopped to think about how your body does, well, everything? Today, we're diving deep into the body's incredible control system. We're going to go from the tiniest electrical spark in a single cell all the way up to the master command center that runs the entire show. It is an amazing story of electricity, chemistry, and unbelievable precision.
All right, so here's our game plan. First, we'll look at the body's #1 goal, keeping everything in balance. Then, we'll find the tiny cellular spark that makes it all possible, see how that spark turns into a message, and then watch it in action during a real emergency. And finally, we'll meet the master control system that's in charge of it all.
Okay, first up, probably the single most important idea in all of biology. You see, everything we're about to talk about today serves one primary mission: maintaining a stable internal world. This is a concept called homeostasis.
Now, the key word here is dynamic. This isn't about being static or frozen. Think of it more like a constant, active balancing act. The body is always making tiny adjustments to keep the environment around our cells just perfect so they can do their jobs and keep us alive.
And just look at everything the body is juggling, all at once, every second of the day. We're talking about nutrient levels, oxygen, waste, pH, temperature, blood pressure, the list goes on. It's an incredible feat of management. So how in the world does it do it? Well, it all starts with a tiny, tiny spark.
All right, so let's zoom way in. We're going down to the level of a single cell to find the source of all this communication. It's something called the membrane potential, and believe me, it is the foundation for pretty much everything that follows.
So, to start, you can picture a cell as being perfectly balanced, electrically speaking. It's got the same number of positive and negative charges on the inside and the outside. The net difference is 0. It's like a battery that hasn't been charged yet. It has potential, but it can't do any work.
But this is where the magic happens. By using a little bit of energy to move just a few charges around, the cell creates an imbalance. It separates positive from negative. And that separation of charge, that creates a tiny electrical voltage. The cell has literally become a tiny battery, holding stored energy, ready to be used.
So how does the cell charge this battery? It's really clever. It uses a pump to push a whole bunch of positive sodium ions out of the cell and pulls a whole bunch of positive potassium ions in. But here's the kicker. The cell membrane is 25 times leakier for potassium than it is for sodium. So some of that potassium leaks back out, taking its positive charge with it. The result? The inside of the cell ends up being negative compared to the outside, sitting at around -70 millivolts. The battery is charged.
Okay, so every excitable cell in your body is basically a tiny, charged battery just waiting. The big question is, how does the body actually use that stored energy to send a message from point A to point B? Well, it does it with two main types of electrical signals.
Think of it like this. A graded potential is like dropping a small pebble in a pond. You got a little ripple, but it fades out pretty quickly. It's a local, short-distance signal. But an action potential, that's like setting off a line of dominoes. Once you tip that first one over, the signal travels the whole distance without getting weaker. It's an all-or-nothing event, which is perfect for sending messages over long distances. And this whole domino effect happens in a flash. First, a stimulus causes sodium channels to fly open. Positive sodium ions rush into the cell, making it shoot from negative to positive. That's depolarization. Then, just as quickly, those channels slam shut and potassium channels open, letting positive potassium ions rush out, bringing the cell back to negative. That's repolarization. This whole incredible sequence is over in about a millisecond. So, when the line of dominoes reaches the end of one nerve cell, it can't just stop there. At a special junction called a synapse, that electrical signal triggers the release of chemical messengers. Those messengers float across a tiny gap and kick off a brand new action potential, a new line of dominoes, in the next cell. That's how complex networks are built.
Okay, we've got the theory down. We know how these electrical signals work, so let's see them in action. Let's look at a critical, life-saving process where rapid, coordinated communication is everything: hemostasis. That's just the fancy word for how the body stops you from bleeding.
The second a blood vessel gets damaged, the body launches this amazing 4-stage emergency response. Instantly, platelets rush to the scene to form a temporary plug. Then, a much more complex process called coagulation kicks in to form a really strong seal. And finally, once the job is done, the clot is cleaned up as the tissue heals. It's an absolutely beautiful, coordinated process.
Now, the really brilliant part of this is the coagulation cascade. You've got all these inactive proteins just floating around in your blood.
But when you get a cut, they get activated one after another in a chain reaction, where each step amplifies the next. And with some help from vitamin K and calcium, it all leads to this. An enzyme called thrombin turns a protein called fibrinogen into these sticky fibrin threads, which form a strong net that seals the wound shut.
So you've got these lightning-fast electrical signals and these complex emergency responses. But who's in charge? Who's conducting this entire orchestra? Well, it's time to zoom all the way back out and meet the master controller of the body, the nervous system.
The whole system is organized really elegantly. You have the central nervous system, the CNS, which is the brain and spinal cord. That's your main command center. Then you have the peripheral nervous system, the PNS. Think of this as all the wiring, the vast network of nerves that carry information to the command center and carry orders back out to the rest of the body.
And even within the central command, there's a clear hierarchy. At the bottom, you've got the spinal cord, handling basic reflexes. Move up a bit, and the brainstem is taking care of life support, breathing, heart rate, all that good stuff. Higher still, you've got relay stations and the main hub for that homeostasis we talked about. And then right at the top, you have the cerebral cortex. That's the CEO. It's where all our conscious thought, perception, and voluntary actions happen.
So there you have it. We've gone from the unbelievably small to the unbelievably complex. From a single ion moving across a membrane to create a tiny spark of electricity, all the way to the intricate structures in our brain that allow us to have a complex thought. It's all connected. A single, seamless, and truly elegant network.
You know, this incredible integration is what makes life possible. It's a system of such staggering complexity, and it really just makes you wonder, what other secrets, what other amazing layers of control and communication is the body still waiting to show us?